Hi everyone, I am Zhehao Sun from University of Science and Technology of China. Today I will be talking about the mechanism design of combinatorial double auction for cloud resource allocation considering group buying discounts. This is the outline of my presentation. Firstly, I will introduce my motivation of applying group buying to cloud resource allocation, and then I will present the challenges of design for allocation mechanism considering group buying, as well as the formally problem definitions. After that, I will detail our design to solve this problem, and analytically prove that our mechanism satisfies some economical properties. The first part is the evaluation, where I will present our experimental results to demonstrate the superior performance of our mechanism in terms of total utility and scalability. Finally, I will conclude this presentation. I first introduce the motivation of this research. Here is the introduction of cloud resource market, where there are providers and users. Providers always process large number of virtual machine instances of different types, like Amazon EC2 or Microsoft Azure, and users always need some virtual machine instances to run his task, such as a web service developer who need a cloud web server to provide service to his users. The trade item in the cloud resource market is the use permissions of virtual machine instances with limited time and a certain number of instances of several types. In the cloud resource market, there are mainly two market-based allocation mechanisms. The first is fixed price mechanism, which is simple and direct, but is not economically efficient and cannot reflect market supply and demand dynamically. Fixed price mechanism is mainly used by commercial companies. The second is auction-based mechanism, in which providers and users are both bidders, and auctioneer will determine winners and price according to all bids. Auction-based allocation mechanism has been proven to be efficient by economic theory, and it is mainly studied in literatures. Except the two market-based model, there is another emerging electronic commerce model which also deserves our attention: group buying. I believe that most of us have been visited a group buying website and know how it works. The characteristic of group buying is significantly reduced prices in condition of minimum number of buyers will purchase the item. Except for being deeply studied in electronic commerce area, group buying is also becoming a new research branch of market-based allocation mechanisms, such as group in the air, which introduced group buying to spectrum allocation by Peng Lin. The motivation of applying group buying to cloud resource market is the advantages of group buying. In a group buying model, providers can benefit from demand aggregation due to the advantage of group buying in attracting buyers, and buyers can enjoy lower price. This is a win-win situation. And what we do is different from Peng Lin, where providers are unknown of group buying and users share the costs to buy a channel they can't afford individually. We focused on the group buying discounts. In our model, providers actively provide group buying rules with discounts and conditions, and the price a buyer should pay is dependent on the group size dynamically. For your attention, this is the first time that group buying discount is considered for market-based cloud resource allocation. Next, I will introduce problem definition and the research challenges. Firstly, I will introduce the allocation model we used. In our virtual machine instances allocation model, there are k different types of instances, which are distinguished by memory, storage, CPU capacity, and network bandwidth. There are multiple providers, each of which offer various types of instances, with different quantity and unit price. And each provider also has his own group buying schedule with discount levels and condition of group size. There are multiple users, and each user requests various combinations of instances to run his task in all or none manner. Here is the notation used to formally define the allocation problem. There are n users, the set of which is denoted as a vector b. An element bi represents a bit of a cloud user. bi is a 3-tuple. The first element of bi is a request vector di, which represents a bundle of instances requested. The second element of bi is length of time requested, which is denoted as ti. And the third element of bi is the user's valuation of the bundle requested, the notation of which is vi. Then there are m providers, the set of which is denoted as a vector s. An element sj represents a bit of a provider. Sj is a 2-tuple. The first element of Sj is a quantity vector, which contains the number of instances of each type offered. And the second element is a unit price vector, which contains the unit price of using an instance of each type for a time slot. The group buying rule of each provider is defined as a discount function, which is a map from the size of buyer group to the discount ratio. The discount function is always a step function, such as the figure in the right. In this figure, we can see that the buyer group can achieve a discount of 20% off when the size reaches 10, and 30% off when the size reaches 30. Then, the final allocation result generated by the auctioneer is denoted as X, which is a matrix with n rows and m columns. The element of X is a binary value, which is set to 1 if it is allocated, and set to 0 otherwise. The final payment of a user I is denoted as Ci. Now we come to the problem definition. Firstly, two formulas are given to calculate the utility of each user and provider, and then our allocation problem is defined as an optimization problem to maximize the total utility of our participants, with the constraints of single-minded user assumption and the capacity limitation for each provider. The objective of the problem is to take full advantage of group buying to maximize the total utility. There are several challenges. The first of which is that our problem is NP-hard because it can be reduced to a classical winner determination problem of combinatorial auction. And the second challenge comes from some perspective of economic, which suggests that there are 3 properties an auction mechanism design should achieve. The 3 properties are individual rationality, which means that no participant's utility is negative; budget balance, which requires the total charges from buyers cannot exceed the total payments to the providers; incentive compatibility, also called truthfulness, means that no participant could be better off by lying. Our problem is different with problems defined in previous work. The problem defined by Lerman is an allocation problem for single-sided combinatorial auction with unique items. The problem defined by Zaman is an allocation problem for single-sided combinatorial auction with multi-unit items in clouds. The problem defined by Samimi is an allocation problem for combinatorial double auction, but without considering group buying discounts in clouds. For your attention, the problem defined by us is an allocation problem for combinatorial double auction considering group buying discounts. Next, I will introduce the algorithm description. Before the description of our algorithms, I firstly introduce the bid density, which is an approximate metric to measure the probability of a bid to be part of an optimal allocation. Bid density may be induced by the value per unit of weight in classical greedy algorithm solving knapsack problem, and is first proposed by Zaman to solve the allocation problem using a greedy manner. In our paper, we defined the bid density as value per unit of instance. Our bid density is calculated by divide the valuation of a bid by the square root of the weighted sum of instances in the bid. We use notation BD to denote bid density. The bid density of a user's bids are easy to calculate. To consider group buying discounts, we define the stable bid densities for providers, which are several bid densities on different discount levels. Below is an example to illustrate the process of calculation and sort. In the example, we can see that each bid of users has their bid density, and each bid of providers has several step bid densities. The number of stable bid densities is according to the discount levels given. After the calculation of bid densities, the bid densities of users are sorted in descending order, and the stable bid densities of providers are sorted in ascending order. There are two phases in our G-step algorithm. First phase is to calculate bid densities and sort. After that, in the second phase, the allocation is generated. Concretely speaking, to every step bid density from minor to major orderly, the algorithm will traverse the sorted list of unallocated users to find the first some users, each of whose requested resource could be fulfilled by the provider of current step bid density. And the valuation is no less than ask price of the provider, considering discounts. Now, let's look into our second greedy algorithm, which is called G-smooth. In the G-smooth algorithm, we use a transformation rather than the stable bid density introduced in the G-step algorithm to consider group buying discounts. The intuition under the transformation is to distribute the discount change, and by this way, the hidden contribution of each attendance to a buyer group can be measured. The figure in the right gives an illustrator. In the figure, D with asterisk is the transformation of a discount curve D, and we can see that after the transformation, the original piecewise constant discount curve becomes a new piecewise smooth discount curve. Given the transformed discount function, we can calculate the revenue increment of arranging a user to a buyer group. There are two phases in our G-smooth greedy algorithm. The first phase is to sort bid densities of users in descending order that transforms the original discount function to a new piecewise smooth one. After that, the allocation is generated by traversing the sorted list of bids of users. To every user, the revenue increments assigned him to each provider will be calculated. Then, the algorithm greedily chooses the one maximize the total revenue of current allocation. After the round ends, algorithm will continue to the next user. It's time to check the winners after the allocation result is generated. Here, we proposed a payment scheme based on the classical victory price, which always charges winner the highest price of the loose bidders. Our victory price is calculated by multiplying the weighted sum of instances of a winner with the highest bid density among the losing users, who would win if the winner is not exist. Then, the charge is calculated by choosing the max one between the victory price and the ask price of the provider. The reason why we choose the max value is to guarantee some economic properties, which will be detailed later. In this page, I will present some properties of our proposed mechanism. The first part is the time complexity. The overall time complexity of G-step algorithm is quadratic, and the overall time complexity of G-smooth algorithm is log linear. The second part is the economic properties, which have been introduced in the challenging section. We have analytically proven that the individual rationality and budget balance are guaranteed by our specifically designed payment scheme, and the truthfulness is also fulfilled because both the two allocation algorithms are monotone and the price calculated by our payment scheme is critical value. Now I introduce the evaluation results. Here we present the simulation results to evaluate the performance of proposed allocation mechanism in contrasted with a previous work, CDARA, which is similar to our SAST model except the group buying rules. In our experiment, we assume that there are 5 providers, 4 instance types, and 100 to 900 users. The parameter setting is detailed in our paper, and here I only present the results. There are 3 performance metrics we considered: total social utility, percentage served, and the utilization. In the figure above, we can see that G-step can obviously achieve higher total utility over other 2 algorithms, and G-smooth slightly outperforms the CDIA. Then in the plot of percentage served, G-step holds the line when the number of cloud users increase, which means a superior scalability, while the other 2 algorithms perform descending tendency. Now I give the conclusion of this work. We fill the gap between group buying and market-based cloud resource allocation, and we model the allocation problem. As a combinatorial double auction considering group buying discounts. To solve this problem, we propose 2 greedy algorithms to generate allocation, and a payment scheme which is inspired by the classical victory price. Finally, the proposed mechanism fulfills 3 important economic properties and have superior performance in terms of total utility and scalability. My presentation is over. Thank you for your listening.